Imagine that today, right now, a spacecraft launches from Earth. Its destination is just one star, not the farthest edge of the universe, not a black hole, not even the center of the galaxy, just the closest star to our sun. But there's one problem. By the time that spacecraft gets there, none of the people watching it launch today might even be around anymore. Maybe our language will have changed. Maybe the countries and cities we know today won't even exist. Maybe human civilization will have been rebuilt more than once. Why? Because the distance between stars is so ridiculously huge that, compared to it, our technology today almost looks like it's standing still. The closest star to the Sun, Proxima Centauri, is more than 4 light-years away. And a light-year is the distance light travels in 1 year, moving at roughly 300,000 kilometers per second. But we're not light. We're a spacecraft. And that tiny difference changes the whole story. The fastest things humans have ever built are insanely fast by Earth standards. But when you're talking about traveling between stars, even those speeds start to look almost ridiculous. Even if we could push a spacecraft to speeds far beyond what our current spacecraft normally reach, getting to Proxima Centauri could still take tens of thousands of years. That means if someone had started this journey thousands of years ago, by the time they arrived today, our civilization might look completely unrecognizable to them. So the real question isn't, how do we build a spacecraft? The real question is, how do we build something that can keep moving for thousands of years and cross distances that are almost impossible to imagine? And that brings us to the first big enemy. Mass. The faster you want to go, the more energy you need. More energy means more fuel. More fuel means more mass. And more mass means you need even more energy just to accelerate the spacecraft, which means even more fuel. It's a brutal cycle. Chemical rockets are amazing for getting us off Earth, but for crossing the distance between stars, it's kind of like trying to cross an ocean in a car. Sure, the car can move. That's not the problem. The problem is how long it's going to take. And this is where things get weird. Back in the 20th century, scientists and engineers actually looked into an idea that sounds like something straight out of a science fiction movie. It was called Project Orion. The basic idea was pretty wild. Instead of constantly burning chemical fuel, the spacecraft could use nuclear explosions to create thrust. Imagine a spacecraft with repeated nuclear explosions happening behind it. Each explosion releases an enormous amount of energy. That energy pushes against a huge plate at the back of the spacecraft, while a system of shock absorbers tries to turn those massive impacts into forward motion. And the crazy thing is, from a physics point of view, the idea wasn't completely nonsense. Actually, nuclear energy is so incredibly energy-dense that it could potentially get around some of the limitations of chemical rockets. But there was a huge problem. Just because something works on paper doesn't mean you can actually build it safely in the real world. Large-scale nuclear explosions come with radiation, safety issues, political problems, and international restrictions on nuclear testing. So Project Orion never became an interstellar spacecraft. But it left us with an important lesson. If we ever want to travel to other stars, we probably have to go way beyond ordinary rocket fuel. And that leads to the next question. If nuclear fission isn't enough, what's more powerful? One answer is one of the most extreme reactions in the universe: nuclear fusion. The sun has been shining for billions of years because deep inside it, light atomic nuclei are forced together under extreme conditions. And when that happens, some of their mass is converted into energy. Now imagine if we could somehow use that same process inside a spacecraft. No nuclear bombs exploding behind us. The engine itself would generate the energy. And if we could turn that energy into thrust efficiently, a spacecraft could potentially travel much faster than anything powered by chemical rockets. And here's the important part. Fusion isn't science fiction in the sense that we don't know whether it exists. We know it exists. The sun does it every second. The problem is that the sun has an absolutely massive amount of matter and insane pressure helping it make fusion happen. We want to somehow put a similar process inside a machine that has to leave Earth and travel through space. The reactor has to be small. It has to be light. It has to be stable. It has to generate energy. It has to deal with enormous amounts of heat. And somehow, that energy also has to be turned into thrust. All of that has to work at the same time. So fusion might be one of our most promising options. But there's still another question. If fusion only converts a small part of the fuel's mass into energy, why not convert almost all of it? And that's where antimatter comes in. For many particles, nature has an opposite counterpart called antimatter. For example, the electron has an antimatter partner called the positron. When matter and antimatter meet, they can annihilate each other and release a huge amount of energy. This is where the famous equation E equals mc squared becomes much more interesting. Mass isn't just something that makes an object heavy. Mass is also a form of stored energy. And if we could convert a huge amount of mass into usable energy, the energy density would be absolutely insane. Compared with chemical fuel, the difference is almost impossible to imagine. But nature gives us a pretty brutal price for that kind of power. We have to make antimatter. And making antimatter is incredibly difficult. The amount we can produce in laboratories today is basically nothing compared with what an interstellar spacecraft would need. And there's another problem that's even stranger. You can't just pour antimatter into a normal fuel tank, because the tank itself is made of matter. And when antimatter touches the walls, you have a reaction. So we have to hold it using electric and magnetic fields without letting it physically touch anything. For tiny amounts, we can do this. But turning that into a huge, lightweight, reliable propulsion system for a spacecraft, we're nowhere close. So antimatter looks incredible on paper. But from an engineering point of view, it's still basically a nightmare. And now imagine something even crazier. Something that doesn't need to carry its fuel in the usual way. Something that could actually get energy from extreme gravity. Black holes are usually the last thing you'd want to get anywhere near. Their gravity is so intense that once something crosses the event horizon, even light can't escape. But back in the 1970s, Stephen Hawking showed that black holes might be a little more complicated than that. Quantum effects could cause black holes to emit a tiny amount of radiation. We now call this Hawking radiation. And there's a strange consequence. The smaller the black hole, the stronger its radiation can become. So an idea starts to appear. What if we could create an incredibly tiny black hole and somehow use the energy from its radiation as a power source? This connects to a theoretical concept sometimes called a Kugelblitz. Basically, the idea is that if you could concentrate an insane amount of energy into an incredibly tiny region, the energy itself could create a black hole. On paper, it sounds unbelievable. But in reality, almost every part of this idea sits right on the edge of what we currently understand about physics. First, we'd have to create the black hole. Then we'd have to control it. Then we'd have to keep it from evaporating too quickly, and then somehow capture and use its radiation. At that point, we're not just building an engine. We're basically trying to control a cosmic phenomenon inside a machine. And maybe this is where we need to take a step back. Because maybe the solution isn't to make the engine more powerful. What if we sent the energy to the spacecraft instead of making the spacecraft carry all of it? That completely changes the game. Until now, we've been assuming that the spacecraft has to carry its own energy. But why? If we can beam energy from Earth into space, the spacecraft doesn't need to carry a giant fuel tank with it. And this is where something surprisingly simple enters the story: light pressure. Photons don't have rest mass, but they do carry momentum. When huge numbers of photons hit a surface, they can produce a tiny amount of force. On Earth, that force is basically impossible to notice. But in space, if the surface is extremely light and the beam of light is insanely powerful and focused, that tiny force can build up over time and push the spacecraft to incredible speeds. Now the spacecraft doesn't really look like a rocket anymore. It looks more like a sail, except instead of wind pushing it, light pushes it. And this isn't just a science fiction idea. Breakthrough Starshot is one real concept that has explored using powerful laser arrays and ultralight sails to send tiny probes toward the Alpha Centauri system. The basic idea is pretty simple. Make the probe incredibly small, make the sail incredibly light, and provide most of the energy needed for acceleration from outside the spacecraft. Some versions of the concept aim for speeds around 20% of the speed of light. If something like that ever becomes practical, a trip to another nearby star wouldn't take tens of thousands of years. It could potentially happen on a timescale of a few decades. But now we run into a whole new set of problems. At those speeds, even a tiny piece of interstellar dust could hit the spacecraft like a bullet. The sail has to be incredibly light while still surviving intense heat and radiation. The lasers would need to produce an enormous amount of energy. And most importantly, we'd have to control that beam with incredible precision across enormous distances. Still, there's one huge advantage. We don't need to invent new laws of physics to get started. We already understand radiation pressure. We already have lasers. We already have ultralight materials. We already have tiny electronics. So this might be one of the few ideas where the gap between crazy idea and actual experiment is genuinely imaginable. But there's still one more idea. And this one brings space itself into the game. What if instead of making the spacecraft move faster, we moved space itself? That's where the idea of a warp drive comes in. In 1994, physicist Miguel Alcubierre proposed a mathematical solution within general relativity where space in front of a spacecraft could contract while space behind it expands. The spacecraft would sit inside this bubble. From this point of view, the spacecraft itself wouldn't necessarily be moving faster than light through its local space. Instead, the geometry of space around it would be changing. It's an insanely cool idea, but there's a massive problem. The original model required extremely strange conditions, including negative energy. And we still don't know whether anything like that could actually be produced and controlled on the scale we'd need. Other models have been proposed since then, trying to get around some of these problems. But none of them has turned into a real warp engine. So for now, we should call warp drive what it actually is. A fascinating theoretical idea, not a working technology. But maybe that gap between theory and technology is actually the most important part of the whole story. So let's put all of these ideas side by side. Chemical rockets, way too slow for practical interstellar travel. Nuclear propulsion, much more powerful but still comes with serious limitations. Fusion, one of the most serious future options, but it still has massive engineering challenges. Antimatter, incredible energy density, but producing and storing enough of it is ridiculously difficult. Black hole engines, absolutely fascinating in theory, but for now they're deep in the speculative side of physics. Warp drive, it could completely change the game one day, but we don't even know if a real version can be built. And then there are laser sails. Maybe the most interesting thing about them is this. We don't need to discover new laws of nature to start working on them. We just need to combine several extremely difficult technologies into one system. Lasers, ultralight materials, miniaturized electronics, beam control, and an incredibly tiny spacecraft. Maybe the first spacecraft to reach another star won't look anything like the giant ships we see in movies. Maybe it'll be tiny. No humans, no huge cabin, no massive engine. Just a small chip, a few sensors, a sail, and a very, very long journey through the darkness. But there's a bigger question. If humanity ever sends the first real spacecraft toward another star, what happens to us? Maybe the journey takes so long that countless generations come and go. Maybe by the time the spacecraft reaches its destination, nobody who helped build it is still alive. But even then, something historic will have happened. For the first time, something made by humans will have crossed beyond the place we've always called home. For the first time, Earth will just be one point along the journey. And maybe the most important part of interstellar travel won't actually be reaching the destination. Maybe the most important moment will be the second that spacecraft leaves Earth. Because from that moment on, for the first time in human history, we'll have sent something toward another star that isn't just meant to look at it from far away. It's actually meant to get there. And maybe generations that haven't even been born yet will be the ones who finally get to hear the answer to this question. What's waiting for us beyond the stars? So if we put everything together, interstellar travel isn't just a science fiction fantasy anymore. We're still a very, very long way from actually reaching another star, but scientists are already exploring different paths. Nuclear propulsion, fusion, antimatter, laser sails, and even ideas that bring space and time themselves into the equation. Maybe we still have no idea what the first interstellar spacecraft will actually look like, but we do know one thing. The distance between the stars is enormous, but human curiosity might be even bigger. And maybe one day, something that's just an idea on paper today will become humanity's first real journey to another star. If you found this journey interesting, stick around for the next videos, because we're going even deeper into some of the strangest mysteries and events in the universe. If you want to know what could be waiting for us in the deepest parts of space, make sure you check out the next videos. And remember, right now, we're still just looking up at the stars. Maybe one day, the generations after us will actually travel toward them.